Sound. What is sound? Why is sound? Well, let's find out. Welcome to my video. If you couldn't tell by the intro, I will be talking about sound. More specifically, the science behind musical instruments, and totally with no bias towards guitars. A quick Google search describes sound as vibrations that travel through the air or another medium and can be heard when they reach a person or animal's ear. While I agree with this, let's make it a little more simple. I would describe sound as waves that travel through a medium. The medium, and no, not the ghost kind, could be anything, from air to water, and yes, even solids. Don't believe me about the solids part? You'll first need to acquire a cat, a box, and deadly poison. Put the cat and poison in the box and seal it. Now the cat is both alive and dead. But wait, you know the cat's alive. You can hear it, or at least for a few minutes. Schrodinger's cat aside, why is this even important? A, to make a joke about quantum physics, and B, explain that anything can be a medium for sound waves to travel through. Now some of you may be thinking, hey, if sound needs a medium to travel through, what medium is it traveling through when there's just air? Well, that's exactly it. It travels through air. So we have learned what sound is and how it travels, but why is sound made? Assuming the medium is air, sound travels by making air molecules vibrate in a sine wave-like pattern that our waves then translate into noises. You may be thinking, okay, but how does our brain translate these random vibrations into noise? I don't want to get into too much biology in this physics project, but here's what Google has to say. We've learned what sound is, how it's made, and how we can hear it. What more is there to learn? Before we truly get into it, here are some words you'll need to know, along with a quick definition. Wavelength. The length for one full cycle of a sound wave, and it's measured with meters. Wave speed, or sometimes referred to as velocity. How fast the wave is moving, and this one is measured with meters per second. And then there's frequency. How many times a wave passes by in a second, measured with hertz. Frequency, or pitch, is how high or low a sound is. For example, compare the two notes I'm about to play. Did you notice how the second note was higher than the first? Here, I'll do it again. Why is one higher than the other? The equation for frequency is F is equal to V over lambda, where F is frequency, V is wave speed, and lambda is wavelength. To change frequency, you have to change V and lambda. Now, we get a little more complicated. So I would like to apologize to you for lying, as the previously mentioned equation is not the equation, but just one of the equations. The equation we'll need for now is the one for strings, as we're talking about a guitar. The equation goes as follows. F is equal to 1 over 2L times the square root of T over M over L, where F is frequency, L is string length, T is tension on the string, and M is mass of the string. How does any of this relate to the earlier demonstration? Well, let's start with the basics. We have the length of the string, which is measured from this white thing called the nut to this metal thing called the bridge. Then there's the tension. The tension is applied to the string by this little peg here called machine. Lastly, there's the mass of the string, which is quite simply how much the string weighs. Using this information, how can we change the frequency of the strings? We cannot change the mass of the string, so that's out of the picture. While we can change the tension of the string, it's very inconvenient to do so in a meaningful way while playing, so that's also off the table. What does that leave? Well, length, of course. But wait, how could you change the length of the string if it's fixed to 2 points? Well, you are kind of right about being fixed to 2 points. You're also wrong. Frets are just little pieces of metal on the neck of the guitar that are very similar to speed bumps. By putting your finger right behind one of these frets, you are changing one of those previously fixed points and are therefore changing the length of the string. Now that we know this, let's look back at the equation and see how this change in length changes the frequency. Using some numbers, let's see how the length of the string affects frequency. Both string lengths will have the same tension and mass. For simplicity's sake, those will both be equal to 1. First, we'll do the longer string. We'll make that string equal to 4 units. When every number is plugged into the equation and the math is calculated, we end up with a frequency of 1/4 Hz. Try to remember that number if you can. Now, it's time for the shorter string. This string length will be equal to 1 unit. After plugging in the numbers, we get a frequency of 1 Hz. 1/4 is less than 1, meaning the string at 4 units will have a lower frequency and pitch than when the string is at 1 unit. Let's do that demonstration again, but now with the knowledge we just acquired. Well, would you look at that? The sound made when the string was longer was lower than the sound made when the string was shorter. So here's an editor's note. Length is measured from your finger to the bridge, just making sure for clarity. Now that we have learned about frequency, there's something else I would like to talk about. Guitars. First, we'll start with the strings. You may have noticed that a guitar doesn't have just one string, but multiple, and most commonly 6. Each string has a different gauge or thickness. This affects the mass of the string. The strings are different gauges so that a lesser amount of tension is needed to get a particular frequency. This is arranged in such a way that the lower strings are thicker than the higher ones. Now you may be thinking, why does the amount of tension even matter? Well, A, so the strings don't break, and B, assuming they don't break, so they don't break the neck. Guitar strings as they are now can apply a force of nearly 200 pounds or 900 newtons to the neck of the guitar. And this is going on constantly. If they were all the same gauge, a lot more force would be applied to the neck. 900 newtons constantly being applied to the neck is still a lot, though. How is this even counteracted? There's a thing in the neck called a truss rod. It is a long piece of metal that is just a little bit shorter than the neck. It can be bent in 2 different directions by turning a screw at the top of the rod. One way is bent with the strings, and the other goes against them. The bend needs to be fine-tuned such that the neck is perfectly straight. This is often done by eye, or with a special straight edge that has notches for frets cut out. With all of that out of the way, let's learn about the guitars themselves. The 2 main types of guitars are acoustic and electric. The thing that makes them different is the way sound is projected and the tone of the instrument. We'll start simple with acoustic guitars. The strings can be made of either metal or something called nylon. The body of an acoustic guitar is hollow and has a hole on the front called the sound hole. When a string is plucked, the vibrations of it are transferred to the body of the guitar, which then vibrates the air inside of it. The sound that was transferred into the guitar is then projected out of the sound hole. This whole process makes the sound louder, as strings on their own are pretty quiet. An experiment you can do to see this in action is actually quite simple, as long as you have an acoustic guitar. First, start playing the guitar and hold it away from your body. Now, bring the guitar closer to your body, making sure you are touching it, and play it. If you listen closely, the second time playing should be quieter than the first, as you are stopping the body from vibrating as much. Unfortunately, I do not have an acoustic guitar to demonstrate this with. Now, it's time for electric guitars. The strings on electric have to be metal, and we'll soon see why. Most electric guitars have a completely solid body, meaning they cannot project sound the same way as an acoustic. To achieve the same effect of a sound hole, electrics have a thing called a pickup. A pickup is a magnet that converts the vibrating magnetic field around the string into an electrical current. This is why electric guitar strings must be metal, and more specifically, a magnetic kind. The electric current is then sent to a thing called an amplifier, or amp for short. The amp then amplifies, or increases, the strength of the electric current. This current is then brought to a speaker, which then converts the current back into sound by vibrating air molecules. This achieves the same effect as an acoustic guitar, but in my opinion, in a much cooler and more versatile way. Okay, so what makes it more versatile?
Well, quite simply, you can just change the properties of the current. A very common way to do this is by adding a thing called distortion. In a nutshell, distortion is achieved by clipping the signal. This is basically just pushing the current past its maximum. In effect, the sound becomes very dirty or crunchy and has a very desirable sound for genres such as rock or metal. Another common way to change the sound is with reverb. Reverb is essentially just making the sound last a little bit longer, but in a way that makes it sound as if you're playing in a large room. This is often achieved by sending the current through an oscillating spring or vibrating metal sheet. This is a very desirable effect for many genres that require a cleaner sound. Unfortunately, this is all we have time for. I hope you enjoyed this video though. If you have any questions, feel free to ask, and I will answer to the best of my ability. Bye-bye!